Okay, so Unit 8 is all about solutions. So, first, let's start with a definition. A solution is a homogeneous mixture which all particles have sizes in the range of atoms and molecules. So let's back up a second. Homogeneous. Remember that the term homogeneous means, well, you tell me. What appears the same, right? Same appears the same throughout. When you look at something, you cannot tell that there are different parts. Right? Effectively, that's what homogeneous means. Now, the size range that we're talking about, anywhere from 0.05 to 0.25 nanometers. Remember when we used to measure wavelengths in nanometers? If we need to, we could convert any numbers back into nanometers. We're not really going to be measuring the sizes here, but that's just to give you reference, okay, about how big these are. All right, so a solution is made up of two parts: the solute and the solvent. Okay, so the solvent is the material that you're dissolving the solute in. So in the case of sugar and water, the solvent is what there's more of, and that's usually going to be water. Right, at least in our labs, 90% of the time the solvent is going to be water. The solute is going to vary, right? Solute could be salt. You can try to dissolve salt in water. You could try to dissolve sugar. You could try to dissolve any kind of chemical, okay? So this varies. And you can actually have more than one solute. You can have 2 solutes, 3 solutes. If you look at the ingredient label on any beverage, you're going to see a listing of at least 10 different solutes, right? The sugar, the dye, the phosphoric acid, like the flavorings, all of those are solutes, okay? But you need both of them to make the solution. The combination is the solution. Now, here I'm showing you and describing you a liquid solution, but a solution does not have to be liquid. You can actually have solutions of gases, of any combination, a gas in a gas, liquid in a gas, a solid in a solid, a liquid in a solid and a liquid. Any combination of those states, those can all be solutions. So, for example, gases and gases, an example of this would be air, right? Air is actually 20% oxygen and about 79% nitrogen, and a little bit of argon, a little bit of krypton, okay? So, but the point is, it's not pure. It is a homogeneous mixture. Therefore, it is a solution. Gases and liquid, this would be like pop, like any kind of pop. Sierra Mist, 7-Up, whatever you like, Coke, Dr. Pepper. Carbonated water is dissolved carbon dioxide. And that's what gives it its bubbles. Okay, so point being, solutions are not limited to liquids. That's the point. Okay. So, now that you know what a solution is, let's talk about how solutions form. So, if a solution is a solute dissolving in a solvent, the only way that happens is if they mix. And so the first rule we're going to bring about is simply called like dissolves like. And what we're describing when we say like dissolves like is molecular polarities. Okay, the molecular polarity of the solute, the molecular polarity of the solvent. Remember, going back to bonding, anytime we drew a Lewis diagram of something, I probably asked you, is this polar or not? And at the time, it may not have seemed that it was important to know that, right? In this unit, it's absolutely important to know that, because that's the only way to predict whether a solution is going to form between two different substances. They have to both have the same polarity. Okay, so they both can, so polar solute will dissolve in a polar solvent, or nonpolar solute will dissolve in a nonpolar solvent. But what you cannot have is the mixing, right? So if I took a polar solute and I tried to dissolve it in a nonpolar solvent, that would not happen. Think of oil and vinegar, right? Oil and vinegar is like the oldest type of salad dressing that exists, right? A little bit of olive oil, a little bit of vinegar, you mix them together, you have Italian dressing, right? They don't mix. If you just let Italian dressing sit there, it separates and you get the oil layer on top because it's less dense, and you get the vinegar on the bottom because it's more dense. And if you want to pour from that bottle, you have to shake it up first, and then you pour it, and then you set it down on the table, and eventually it separates out again. Okay? Oil being nonpolar, vinegar being polar. That's why they don't mix. Okay? All right, so how do the solutions form? Attractions. Attractions between the solute and solvent cause solution formation. Okay? If two liquids are able to dissolve, then we say that they are miscible or soluble. But miscible is a better term. Miscible means the two liquids can mix. We just mentioned oil and vinegar. They do not mix. So oil and vinegar would be considered immiscible. They don't mix. Okay, so ionic solids behave as polar molecules. Even though they're ions, they behave as polar because they can dissolve in polar solvents, right? Which is why we have salt water. Salt is ionic. Salt dissolves in water, which is polar. That gives us salt water, which is a solution. So let's take a closer look at that. This picture here shows us a crystal of salt. So this structure where we alternate positive, negative, positive, negative, positive, negative, this structure here is what we call a lattice. I don't know if you remember that term. Okay, a lattice is a repeating array of particles. A repeating pattern. In this case, the particles are ions. So, if I took salt and I dissolved it in water, I'm hoping you remember water is a polar molecule, and any polar molecule is going to have partially positive and partially negative sides. So let's zoom in here in this picture. Each one of these water molecules, right here, that's the partially positive side is the hydrogens, right? You guys see that? Each hydrogen is listed with a delta positive. That's a partial charge. The oxygen side is partially negative. Okay? So, every water molecule has a partially positive and negative side. If I were to draw it here on this one, this would be delta positive. This would be delta negative. Now, the reason why I'm bringing that up is because when you look at the salt crystal, the attractions that exist here, attractions can only exist between opposite charges. So it makes sense that the positive ion is being attracted to the negative side of water. Right? however many water molecules doesn't really matter. The point is, it's the negative side of water that faces the positive ion. And then when you get enough of these water molecules attracting the ion, that ion is pulled off. It just pops off. Okay? Now, let's look at chloride. Chloride is a negative ion. Water's positive side is attracting the negative ion. Same thing. If you get enough water molecules attracting this chloride ion, it's going to get pulled off. And so what's going to happen is slowly, layer by layer, the salt crystal is going to get smaller and smaller and smaller as more and more of its layers dissolve until it's completely dissolved. And the primary reason is this attraction right here. The attraction between the polar molecules and the ions. It pulls the ions apart. Okay, this process is defined as dissolution or solvation. Both those two terms mean the same thing. They both mean dissolving. It's a technical term for dissolving. Okay. All right. So at this point, if I ask you, how does an ionic compound dissolve? Can you explain it? Christian, can you explain it? Just generally.
Ionic with a polar.
Okay.
Because it acts as if it's polar. Create a solution because it's pulled off until it's minimalized.
It's pulled off. The attractions between the water and the ions cause the ions to get pulled apart. That's it. Yeah. Okay. So, what if we have a different type of solute and solvent? Non-polar and non-polar. I'm going to have to add a page in here because I need more space to draw a picture. Okay, so if we have non-polar solutes in non-polar solvent. First of all, what does that even look like? A non-polar solute, think of wax, like a chunk of wax. Wax particles are nonpolar, and they're large. They're large and nonpolar, which means the only attractive forces they have are dispersion forces. Okay, so it's dispersion forces holding them together. So, if I were to plunk this into a non-polar solvent, let's make the non-polar solvent here green. What's going to happen is that the solute and the solvent, they're not attracted to each other. Not like water was with salt. The attractions here are very minimal. So first, let's understand that. So minimal attractions take place. So if they're minimal attractions, they're not attracting each other, how does the solution form? Well, it's because the motion, the energy, the kinetic energy of the liquid molecules constantly bumping into and battering the solid, they eventually cause these wax particles to loosen and then pop off. Imagine a cabin built out of Lincoln logs. When you build a house with Lincoln logs, how do you get them to stick together? Do you glue them? Do you screw them down? Do you nail them? No, you just stack them, right? So think of a nonpolar solvent like that. And let's say that you had a bunch of bouncy balls, and you kept tossing bouncy balls at this Lincoln log house. Eventually, that Lincoln house that house is going to crumble, right? And so that's kind of the same thing that happens when you have a nonpolar solute in a nonpolar solvent. But it's not based on attractions. It's entirely different. So there's two different ways that how things dissolve. It depends on if it's polar, or it depends if it's nonpolar, because the two things are different. Okay? All right. So, some examples of nonpolar solvents. Turpentine, which is known as paint thinner. If you guys have ever painted with oil paints, all right, you know that you can't wash the brushes with water. The paint will not come out. You have to use what's called paint thinner. And so what that looks like, it's usually a jar, right? So imagine you have a paintbrush, right? And it's covered with paint. You dip this in a jar, and then you wait like a day. And then when you take it out, the oils have been dissolved by the nonpolar solvent, and then the brush looks completely clean. Right? Now, if you paint indoor, like when you go to Menards and you go to Home Depot and you buy paints, there's essentially two types of paint. There's water-based paints, which are used indoors, and then there's the oil-based paints, which are used outdoors. Right? Outdoors, what happens outdoor? It rains. Paint, oil is nonpolar. You want water to just fall off and roll right off the paint, like a fence, a garage, right? But there's no real threat of rain inside your house, so you can use water-based paints, and it's a lot easier to clean the brushes. So that's easier, it's faster to apply, it dries faster. There's a lot of benefits to using water-based paints, right? Oil-based paints are only used when they have to be, or if you're an artiste, right? And you actually do want like all those fancy colors, because you do get better colors with oil-based paints. All right, well, you use some of these too, like hexane, octane. Octane is gasoline. They used to use gasoline to paint brushes back in the day because it's what they had around. Like they had gas can, they paint, a farmer just finished painting his barn red. He's got all these brushes, just dip them in a can of gasoline and they'd be clean the next day. It's also flammable, so you had to like leave it ventilated. Okay. Electrolytes. We talked a little bit about electrolytes back in our bonding unit. Definition. Electrolytes are solutes that when dissolved cause the solution to conduct electricity. So what is electricity? Electricity is moving electrons. So any solution that contains charged particles can conduct. I'm going to wedge in here some qualifications. In order to conduct, there's two qualifications. One, you must have something charged. So that means ions or electrons. Two, the particles must be able to move. They must be mobile. Like a solid is not mobile, it's immobile, so solids don't conduct, right? But ions, when you dissolve them, when you melt them, they do. So therefore, most electrolytes have ionic solutes. And it's pretty easy to test because you just get yourself a conductivity tester or one of these, and I'll show you here some examples of that in just a second. Okay. Okay. So I'm going to stop this here, and we're going to start talking about our lab.